Thank you very much. Yeah, I changed the title slightly. I thought since this is LA and I share a hometown with Arnold Schwarzenegger, I feel entitled to do this. So what I'm going to talk about is when you look back at how we did medical imaging, at the invention of medical imaging, it is a very, very expensive piece of machinery operated by highly skilled, very expensive people. And then this is sent to some workstation using some math that was there at a time. And then you get some image. Back then, they were absolutely amazed by it. Nowadays, we just laugh at the image quality. And then is sent to another set of really highly trained people who look at it and say, OK, this person has a stroke or no stroke or pneumonia, whatever. So when we look at what we are doing today, now we have really come a long way. So the images we get are something like this. So I mean, you can see the fibers in the brain, and it's all amazing. And we're very, very proud of these images. But when we look at the overall pipeline, we are still doing is we have a very, very expensive piece of machinery. It's operated by highly skilled people. It's not trivial. Then we send it to a workstation. We, at least clinically, use pretty much the same math that was used 30 years ago. And then also, it's sent to a couple of people who look at it and then make the decision. Difference is now they look at it in computer workstations instead of plain films, but that's about it. And what I'm going to talk about is when we consider all the new advances and the compute capabilities that we have, the developments in optimization, machine learning, deep learning, artificial intelligence, how can we use these tools to enhance the features in every single of these parts? And in particular, I want to cover the imaging hardware, how we measure the data, how we reconstruct the data, and then how we interpret it. And then, hopefully, how we can tie this all together within the scope of modern compute methods. And I'm going to focus a lot on image reconstruction because that's where I'm coming from, but I will cover all of these other parts. Also, if anybody has any question at any time, what's your policy? I mean, feel free to interrupt me. It's fine for me. Yeah. It's OK? OK. Just wasn't sure about the recording. I want to point out that pretty much all of this is a collaboration with Graz University of Technology, the Computer Graphics and Vision Institute, and with Facebook AI Research. So just to give you a little bit of a primer, since this is not a classic MR audience, one thing, and that is a common theme that I will use in this talk, is we are acquiring our data in Fourier space, which means so an MR scanner is really a scanner. So you excite the tissue with radio frequency, and then you measure one line of Fourier space, then you wait a bit, then you excite again and again and again, and you build up this data space in Fourier space. And then when you have this done, essentially what you need to do is you need to do an inverse Fourier transform. So this is the forward encoding model. It's just you have these Fourier terms there. This is the coil sensitivity is part of the receive pipeline. And then essentially the image reconstruction is this inversion of this linear system. And then when you measure all the data, you do your inverse Fourier transform, you get a great image. So if you want to accelerate this, and let's say you want to sample instead of 10 minutes in 5 minutes, you measure every second line. That's trivial to do in a way. But then when you do the same approach, then you get imaging artifacts. Right? You violate the sampling theorem. It's completely obvious. You get a useless image. But this is a way to very easily speed up the MR acquisition. And anybody in the room who had an MR yet? Show of hands. Great. It's not a particularly pleasant experience, right? How long did it take? 30 minutes? 20 minutes? Lie completely still? Very noisy, loud. So imagine you could do this, for example, in a 3-4 minute, and then you're done, you're out. You don't have to hold your breath. So all of these things come with making the MR acquisition faster. And one of the not early developments, but about 10 years ago, people started using compressed sensing. Notice that MR is a great application for compressed sensing. So you essentially you have the same matrix inversion problem here. You solve this quadratic optimization problem, and then you just add some regularizer term that separates the image information, the image you actually want to get, and the artifacts, and you want those to remove. And if you are considering a simple example, so let's say my image looks like this, and I have Gaussian random noise corrupting it, then doing something like total variation, you don't really need to look a lot further than that, in my opinion. I mean, this is a great image model for a cartoon image with Gaussian noise. It does a really, really good job of separating those two. But because our images are a little bit more complicated, and also our aliasing corruption structure is more complex, we thought, okay, how can we go beyond this? And then obviously another thing that you need to do when you solve or try to solve such a problem, you need to have some numerical implementation. So you write it down as an optimization problem, you have some cost functional that you minimize, you need an iterative method. So many flavors to it, of course, and most of you in this room know a lot more about it than I do, but you will calculate a gradient of this and then have some kind of update iterative scheme where you move in the direction of the gradient. And in the end, when you have solved your iterative procedure, you will have obtained your clean, uncorrupted image. So far, so good for everybody? Okay. So when we thought, how can we generalize this, how can we extend this, and this led to machine learning, was instead of using some handcrafted prior model, let's build our forward model in our data acquisition and then learn a regularizer specifically that separates the type of artifacts that we get from the image that we want to obtain. And so this, you can reformulate for example, the gradient in total variation, or the sparsifying transform, like the compressed sensing people call it, as spatial filter kernels, and then generalize the norm that you use to penalize this. And this comes from the field of experts regularizer model, this generalization of TV. And you can write down the same optimization problem like this. Now you have this new, highly or more powerful computationally a regularizer term. And then the question is how do you obtain these parameters? And also when you put this in this numerical optimization scheme, again, what you need to do is you need to do a series of gradient descent steps where you put in your input data and all the other information about the system that you want. But you need to calculate a gradient, and with this particular model, this gradient, you can calculate it analytically. It just has exactly this form. And then you can write this out as a neural network where, and the nice thing about it is that you don't need to do any magic handcrafting of the architecture. It essentially, the network designs itself. You need to essentially, every single gradient step needs to have this form. And you end up with this structure that we call variational network, because essentially every single network layer does a gradient descent step. And then the question is, how do you train it? How do you obtain your filter parameters, your activation functions? And that's also pretty straightforward. You just do it in a supervised way. So you have your measured ground truth data, and I assume that I have it for now. I will come back to that later, because there are situations where you... It doesn't really matter. You can do it Cartesian. It depends on the application. You can do it... You have complete freedom how you sample k-space. It's just you put some magnetic fields to your gradients. You can sample this radially in spirals. You can do 3D rosettes. This, for the sake of this, I'm using the simplest thing. It's just equidistant Cartesian where you skip some lines. You can do it a lot better, but for these type of acquisitions, we are a little bit constrained by the imaging physics of the sequence. So doing this with a radial trajectory or a random trajectory is actually not so easy, because it's 2D. And also, to obtain this image contrast, you are somewhat constrained. But we can talk more about it. Any other questions? Okay. So you put this data in there. Then you have some initial model parameters. You get some initial output. It has some artifacts, obviously. You compare this to your ground truth reference. You get some similarity measure, and then let's say you just do the mean squared error. You are minimizing or looping over all the training examples that you have, compute the error between your current network output to your reference, and then you minimize this, and then you loop over your whole training set and update the parameters of your network. Very classic supervised learning. So here are some examples that we got. Those are from the paper 3 years ago. And what made me really excited about this was because I've been doing compressed sensing, constraint reconstructions for a very long time. And you usually have this trade-off. You have a regularization parameter, and you have this trade-off between how strong do you weight your prior and how strong do you weight data consistency. And it's usually either you are losing small, fine details, or you have lots of artifacts left, or lots of noise. And in this comparison, what you see here, so this is parallel imaging. So this is an iterative method that uses coil sensitivity. So this is the standard in clinical practice at the moment. When you go to an MR scanner and they measure you, and so this is the algorithm that they will use. This is a compressed sensing extension of this. So this is a nonlinear regularizer. It's a variational penalty, total generalized variation. And this is the machine learning version of it. And what you can see there, I hope it projects, is that first of all, there are some residual aliasing artifacts there that are removed pretty efficiently with the machine learning method. But it preserves the texture better. So you actually keep more fine details while removing more artifacts. And that got me really excited because it was always this trade-off between these two before. And you can see it even better when you zoom in. And so this was an example. When I showed this to the clinical partners, that was the time when they got interested. So the crazy math physics people are coming up with something again. And, oh, no, this might actually be useful. So here, this is a very, very tiny pathology, damage in the cartilage of the knee. And I think you can actually see it a lot better here than in the compressed sensing reconstruction. And obviously, parallel imaging reconstruction is super noisy. So this got the clinical attention, and then we could measure lots of data, and people were interested. So that really helped spark interest in this. The question is, how well does it generalize? So this is an example of clinical knee protocol. So you don't measure only one sequences, but 5 sequences. So for example, you have multiple orientations. This one is cut through the joint like this one like this, and this is sagittal. And you also have different image contrasts. All of these have slightly different SNR. And what you see here are reconstructions that were trained with every single contrast being a different model. So this is a model and a reconstruction that was trained entirely of images that look like this, with this contrast, with this orientation. And same for the other ones. And these are structural similarity, by the way, just for this particular one slice. So it's not for the full test set, but it is the same, it generalizes. Oops. And this is what you get when you train one single model on all of these examples. So that I found encouraging. Obviously, that's not super well evaluated clinically, everything, but it tells you that you can actually train one model that has the computational capacity to successfully reconstruct images with somewhat stronger variety, different contrasts, different orientations. And then other people have started doing this as well. So this is an example from Stanford. They actually tested it with clinical patients in the abdomen and have shown that you have improved sharpness and preservation of fine details while preserving SNR. And this is an example from King's College, Claudia Prieto's group, where they have done it for coronary arteries, and again got very, very similar results. So one thing that bothered me a little bit was when this started out in 2016, roughly, that the number of papers that did something of this flavor really, really exploded. But the problem I always had with these papers was they looked something like this. Like, we tested it on 10 clinical patients, so this was ours. So I'm not pointing fingers at others, it's us as well. Then another one healthy volunteer, 27 patients, 7 subjects, 10 subjects. So all of these papers, they used their own internal data, trained their models, presented their method, showed the results. So for me, as somebody who tried to observe the field, it was absolutely impossible to compare method A with method B, because they are own for, like, everything was done for one particular application with their data. The data is not made public. So you really have no way to see how do these methods actually compare. And if you compare this to what the computer vision community has, they have these really, really nice benchmark data sets where if you read in a paper that somebody has an error or a structural similarity, whatever, on ImageNet, then you pretty much know the ballpark where it operates. But something like this doesn't exist in medical imaging, at least not for image reconstruction. So what we did in 2019 was we organized this, what we called Fast MRI Image Reconstruction Challenge. So we put a data set together from NYU. So this is raw measurement data from the MR scanner. So it's not the images, it's the Fourier data at the stage before the scanner processes it. About 1,400 cases from clinical patient, from knees. And by the way, we just added a month ago neuro or brain data to it, 7,000 raw data cases. If you're interested in this and haven't seen it, this is the webpage. You can download this. There is no restrictions or anything. Everybody can use this for free for research. And then we designed a reconstruction challenge. So we gave people a training and a validation data set, and then also a challenge test set where we only gave them undersampled data. And these are the sampling masks now. So this is a little bit different. So this is now pseudo-random sampling. And then they did their reconstructions, sent them to us. We compared it against the ground truth and then made a leaderboard. And in that way, I thought, okay, that's really an opportunity to see where the field is as a whole and let all these different groups compare their methods on one standard benchmark data set. And then we did 2 things. First of all, we did multiple tracks. So we did one track where we operated at a level that is representative of what you can do in the clinic at the moment, or try to accelerate twice as much as in the clinical standard. So you just try to see what you can do with this. And so these are the number of submissions that we got for this track. Then we had one track where we wanted to push models really to the limit, so it's 4 times faster than the clinical standard. And then we had one track where we were not so much targeting the MR audience, but the classic or data science, machine learning, image processing audience, where we didn't have this multiple coil aspect, so it was just single case base or image. So anybody who wanted to do purely image processing approaches could use this. And as you can imagine, we got more submissions to this one just because the entry level for this is a little bit lower. And then we did a 2-stage evaluation. So these are, in the first stage, we calculated structural similarity. And these are the plots of structural similarity of the different submissions for the different tracks. This is a screenshot of the leaderboard. And we took the top 4 submissions of each track and sent them out to a panel of radiologists, because ultimately they are the experts, you would believe. And not only from NYU, but throughout the country. And then they rated the submissions, and that's where we decided who was the winner in each track. And it's quite interesting when you compare the quantitative scores of structural similarity with what the radiologists like. And there were some trends were interesting. So for example, so this is just a scatter plot. So this is the radiologist score, and this is the quantitative score. And for the multi-coil 8 times accelerated, they actually correlate pretty well. So both structural similarity and the radiologists predict the winner. Here it's not so great. But for the others, they are pretty much all over the place. So that there's not a real strong correlations between the quantitative metrics and also those that were used to optimize these machine learning methods and what humans observers really like to see. The problem is, you could say now, okay, let's get rid of these metrics. Let's all work with radiologists, show them images, although then I don't know how you would do machine learning, because that would be a very slow training loop. Not even the radiologists could agree among themselves. So, for example, there were 2 tracks where at least the winners were somewhat consistent, but then again, with the other ones, they didn't really agree. But here, it's almost random. So for example, the last place submission was actually rated the best one by 3 and the worst one by 4. So what do you do with this, right? Who do you trust? And that is a theme that I will have throughout this talk, is that it's really, really hard in medical imaging applications, in my opinion, to really define what is a good image. And not even the people who do this all their life looking at these images agree on what is a good image. That makes it really hard. So here are some examples. As you can see, they all have pretty amazing image quality. So these are the top 4 submissions. This is the from Philips, Philips Healthcare. This is from United Imaging, so another company submission. This is from Imperial College, from Kerstin here. And this was from University of Amsterdam. To me, they all look the same. And maybe that's the reason why the radiologists also couldn't agree, because in the end, it was pretty subjective. What is interesting, though, is this is another example, and there are a couple of things that people worry about when you talk to them about machine learning for medical imaging, for reconstruction. And one of them is, what happens if you have a gross abnormality that's really, really very strange? Will it completely break down? So this is a case that I found that has a severe artifact here, because this is a person that had surgery. So there is some metal implant there that creates like really, really severe distortions that are really abnormal. So this looks nothing like a healthy knee, obviously. And none of the methods obviously there is still these artifacts. They will not remove this, but they work completely fine. So actually that was something that I found very reassuring, especially not only because it's not only my result, but the result from the whole community. On the other hand, what is more on the worrying side, so this is a case that has pathology, and this is a subtle pathology, but it's a very, very common pathology. Like this pathology was present in the training set all the time. But it's a very, very small little feature. It's a meniscal tear. It's this tiny little bright line that you see there in the cartilage. So that's the pathology. So all of these, in the accelerated reconstructions, you don't see it anymore. And that's really the type of error that worries me. It's not the part where you think the model falls apart completely, but that you can immediately spot. And the radiologist would just say, yeah, okay, scan it again. But this is worrying, because then you suddenly look at it, think, oh yeah, that's a pretty good image. I'm confident that I can make a diagnosis of it, but then you miss the pathology. So that's a really critical part.
Even if you train the feature, the same thing happens?
You mean if you do pattern recognition and try to detect the pathology?
Focus training, that part is somehow
Nobody, I think, has tried this. I think it's pretty much a matter of, so you are losing high high frequency, because this is where you don't measure your k-space. So at one point, there's simply probably no data that supports this. And the model, there's two ways. Either the model could blur this out, or the model, especially if you use a generative model, could interpolate some features that it saw in the training data set, but probably, or that is my guess, they wouldn't be representative of the data that you measure. So I don't think this is a machine learning problem. This is simply that in this case, you don't have acquired enough data to recover this high resolution. The tricky part is that with machine learning, suddenly you get great looking images that you think you trust. Whereas if you do regular parallel imaging or something, you get something that's completely noisy and or completely blurry, and you see, okay, I cannot make a diagnosis from this. Yes.
I have a question. So when you give the data set, you do some kind of down sampling, that's right?
Correct.
So if you change the down sampling strategy, this can be saved. If you could be different kind of random sampling.
I would, if you knew this up front and tailor it, then I would say yes, this is probably true, because then you could see, okay, which spatial frequencies do you need? But in practice, if you don't know what you measure, so are you thinking about adaptively trying to change which k-space points to sample and then training with this? Yeah, you can probably improve it.
That's what I try to see, because your down sampling strategy means
yes,
because,
yeah.
It's not because of machine learning, it's because the data set is missing.
Correct, yeah. But there will always be a point when you push it too far and then the information is gone. And I think no matter what you do, it will save it, unless you know up front what you want to see, which is not a particularly exciting situation. My take-home message is simply that the complicated part is that you can create images that actually look amazing, but the distinctive feature is missing. You had a question? Yeah.
So I was just wondering, I mean, to me, since all the methods fail to find this feature, I mean, I tend to believe you that it may not be in the data.
Yeah.
So have you guys thought about any ways to quantify or to test this hypothesis? So for example, with uncertainty quantification methods, you should probably be able to detect that in this region, your estimates have a very high variance.
Yeah.
Because I mean, I like actually your interpretation. If you have a very noisy image, the uncertainty is kind of encoded in the noisy image.
Yeah.
Now that the image looks clean, maybe is there a way to?
Yeah. So I fully agree with you. We haven't done it yet. I know that there are several groups who are working on it, and the way I see this, how this could be useful, exactly what you're describing is if you give a doctor not only the image, but let's say a variance map, where you can say, okay, these are parts here that are very strongly supported by the data. And these are parts where a lot is coming from the model. And then you see, okay, maybe I can trust this region more, can trust this region less.
And a follow-up question would be like, do you think radiologists would appreciate those images?
So that's a very, very tough question. And it's a question of training. The current generation of radiologists, the older ones, they are very conservative, so I think they would be hesitant. They want something, just give me one image and I know I can trust it. But the newer generation, I think they are much more open to things like this. So I think this is a gradual progression.
This also comes to me, let's say you have 10,000 cases, but you have rare disease. Let's say 1 or 2 cases have rare disease. Probably you do this machine learning, the rare disease will disappear.
There I'm not so sure, because so this is actually what I was, so remember we are not doing disease-specific classification.
Yeah,
so we are essentially what we are learning is this, we are learning the separation of the artifacts that are created by the forward model. So of course to some degree they depend on the image content, but they are not very specific. And this is actually what made me more confident about that this situation is actually better taken care of, because this is a very Well, it's not super rare, but it's still, it's very abnormal, it's very different, and the models didn't have any problem. I think it's mainly small features that suddenly disappear below the noise level, and those you can't recover anymore.
It's something like oscillating several times in the small region, and the machine learning may not catch.
Yeah. I think I'm leaning myself very, very far out of the window saying that this will not be a problem, but I am much more confident about the, if it's a certain specific part or anatomical variation, pathological variation, that the model will actually not struggle so much with this, but in general just a matter of preserving resolution, fine details. But that's entirely my own opinion, and it's not backed up by any studies or analysis.
So would it be reasonable to do a pre-processing where there are landmarks that are provided by specialists that already know where the usual pathologies show up?
Yeah.
So that then you're actually discarding the data that you're not going to end up using.
Yeah, that's an interesting idea. I mean, the tough part of this is that this requires a huge amount of effort in data curation, and it requires data curation by radiologists who are expensive.
Yeah, but landmarking is like a field analysis.
But you still need some ground truth labels, right?
Yeah.
So, and those are hard to get, in my experience. Like if you ask your radiologist, can you label me 5,000 meniscal tears? I'm going to just say it's not going to happen. But that would be great. That would be great. And one of the things that I'm hoping when we release this data set is that people do exactly this. Like it's maybe we can make this a crowd community initiative that maybe every radiologist labels 10 also. Will be a little bit of a noisy data set, but still be a lot better than what's out at the moment. Okay, that's okay. So now let's go a little bit from reconstruction to, with these technologies in place, how can we change our data acquisition a little bit? And one of the things, or an example that I would like to show you is dynamic imaging, where you inject a contrast agent that over time dynamically changes the contrast mechanisms. And the way this is done in the clinic at the moment is you are doing one scan as the pre-contrast measurement, then you do a timing run because you inject the contrast agent, let's say here, and then you want to see when does it arrive here. So you see how long does this take. And then you inject the contrast, and then after a certain fixed time delay, let's say 20 seconds, 60 seconds, you do a couple of phases. Like this is the phase where the contrast agent is in the arterial system. This is the phase where it's in the venous system. And then maybe one in the end. And obviously, if you mess up this timing, then the whole exam is essentially screwed up. In each of these, because this is, in this case, an abdominal exam, the patient needs to hold their breath. So if they fail to hold their breath, imagine holding your breath for 30 seconds when you're actually sick. It's actually not so easy. And then one of them is corrupted, and then it's not so easy to redo this exam because you don't want to inject another round of contrast agent. And this is really, from a workflow point of view and also from a patient comfort point of view, this is pretty challenging. But it's done clinically all the time. So one thing that we have developed at NYU a while ago is this continuous radial acquisition where you just sample during free breathing, and what you get is essentially a real-time video type of sequence of MR images while the contrast is injected. And then you can at the stage when you reconstruct the images, then you can group them together for the certain time frames to have this trade-off between temporal and spatial resolution. So this is on the acquisition side. So let's say we want to use a similar approach with machine learning reconstruction that we have done before. It is a little bit challenging, and this is an open question on an ongoing project that we have. So, because the question is, what is your ground truth, right? So now suddenly you either have high spatial resolution or high temporal resolution. So if I make the time slots short, then I have very, very fast, let's say, 2 seconds, 3 seconds temporal updates, and I can capture these dynamic curves pretty well. And this is, for example, how this would look like. So you really have these sharp peaks in the arterial system that you want to capture because they are very, very important for the specificity of certain tumors, like how fast does the contrast agent enter the tissue. But the images look completely crappy. On the other hand, what you can do is you average more together and then the images look great. But you simply don't have both. And there are lots of things going on at the moment in this field. So one thing that we are doing at the moment is we are doing numerical simulations of these contrast kinetics and then try to do transfer learning from simulated data to real data. But then how well will this generalize? Nobody knows. Another idea is to do unsupervised learning. Some people are doing this. I have yet to see something that really not impresses me, but this is really, really challenging. Also because we don't have so much data. We don't have 1 million of examples. And then also, with this type of acquisition, how do we design a regularizer that has this spatiotemporal nature of the data in mind? These are just some preliminary examples focusing on the last part. So this is, these are 5 time frames. So you can see this was before the contrast agent injection. The tumor is right there. And this is at some later frames. They have a time resolution of roughly 8 seconds. So you can capture the contrast dynamics pretty well. This is where the lesion is. And this is what you get when you use the exact same variational network model slice by slice, or I should rather say frame by frame, that I have shown you before for the knee images. And this is what you get when you use one that is spatial temporal. So it has convolutions over the time domain. And I think it's pretty obvious that these look a lot better. You remove more artifacts, they're a lot sharper. The challenging part then is what you are actually interested in are these dynamic uptake curves. And then you can plot this, and what you will see is, so this is for, the red one is for the malignant lesion. So this is where the tumor is aggressive. The blue one is for healthy background. And the solid line is for the model that has a spatial temporal regularizer. The dashed line here is just a conventional non-uniform Fourier transform, and the small dashed line is the model that has is learned but is done frame by frame. And what you can see is that the images look a lot better, but now you really smooth out this curve. But what is the real curve? I mean, we don't know it. I mean, and that's we're looking into this at the moment with simulations where we have a ground truth and we see how close do we actually get. And then the real test will be to calculate pharmacokinetic parameters, like the simple differential equations that describe how well or how fast does the tissue, the contrast agent diffuse from one part of the tissue to the other one. What I like about this is that since I mentioned how challenging it is to do evaluation, when you just look at images, here we actually have a quantitative measure. So we can simulate with fixed contrast enhancement parameters and then compare, do our quantitative measurements, are they consistent with the ground truth? So that's a little bit more of a harder evaluation than just looking at images or even having radiologists look at images, because you have seen that there are cases where they not even agree. Moving to the last part of the diagnostic chain, this is classification, and this ties into this question of how should we evaluate. And sticking with the theme of breast cancer, we have some work on image classification, and in particular what we want to do is we want to predict breast cancer. Either is there a benign or a malignant lesion present, either in the left or in the right breast. And we got a pretty large data set together, 8,000 cases from NYU. And then, yeah, it's simply a classification problem where you try to maximize the log likelihood of the presence of pathology. our architecture is pretty straightforward. It's a standard ResNet model. The only thing that we do different is we do separate ResNet models for the different slices and then concatenate those together, then use another ResNet to pull those features from the different slices together. And then we have these four binary tests, like left breast, right breast, malignant, benign, either yes or no, is the lesion present or not. So that's the task we're trying to solve. And so this was presented at the NeurIPS medical imaging workshop by Shizang Gong. So he's a student from NYU. And we get pretty decent AUC curves with this. They are a little bit better for the malignant case than for the benign case. The reason for that is simply because our benign labels are more noisy. So our ground truth here is biopsy, pathology. And for the benign lesions, they are sometimes cases where they are not even sent to pathology. So then that doesn't show up as a lesion. So yeah, our labels are noisy. But what I really want to put the focus on is that if you have this reconstruction machine learning approach and you have this classification approach, then you are really looking at, okay, what am I really interested in the end? Like not so much does my image look good, but really what is the diagnostic information output that I can get from this set of data. So you can imagine a pipeline that looks like this. I take my undersampled case-based data, I put it through my reconstruction network, I get this image. It may be good looking, bad looking. I have my reference or whatever I use. I calculate my image-based error metric, just the way you saw it before. But then I put this through a classification network that gives me exactly the clinical question that I want to answer. And I have my ground truth labels from biopsy. And for example, this one has both a malignant and a benign lesion in the left breast here. Radiologists always look at images from below, so that's why. I don't know why.
So Florian, why have the image-based error metric? In the end, you care only about the prediction.
So what we would do in practice is something like this. So you have a hyperparameter that balances between the two. What we saw is that if you don't have it in there, then this is really very unstable. So you need this as a little bit as a guidance in the training of the model. You can set it to 0, of course, and then you are. And this is an open question. Yeah.
No, because I mean implicitly you say that the image that the classifier sees should look good in whatever we think is good, right? But the classifier may not agree.
So this is a great question, right? And this is, I find, really exciting because this goes beyond the classic imaging pipeline where we optimize everything with respect to a human looking at the screen, right? Whatever is important for us in an image may be completely irrelevant for a machine learning classifier, but it may also see features that we do not see. Yeah. So I was really, really curious when we tried this out, and I was wondering, do we even get an image? So this is a super preliminary example, but this is we really tried to push it to the extreme here, so the image looks pretty terrible, like lots of noise, very high acceleration. But this is what you get with a separate model that is trained for reconstruction, and this is what you get with end-to-end. Does it look better? I don't know, but at least it looks like an image, right? But, you had another question?
I want to go to the previous slides.
Mm-hmm.
So you build your classifier based on reconstruct the image.
Mm-hmm.
Did you try to build your classifier directly on the full resolution image and see the difference between the two?
Yeah, so this is essentially this result, right? So this is, of course, it works better. I mean, no doubt about it, yeah. But it's essentially what you're exactly right. So this is the experiment that you need to do, right? So build the classifier from this, build the classifier from the trivial reconstruction, see how well the classifier performs, then train them together, and then your result will be somewhere in the middle between those two. And ideally, you want it to get as close to the classifier of the fully sampled reconstruction. Yeah. So that's ongoing. Yeah. That's exactly the experiment or the validation that we want to do. And then finally going to the other side of the things, when we start questioning like what image features are actually important, are there some things that we have set for granted, right? When we have been designing these machines for the past 30 years, right? You build this $10 million machine, and it's super highly spec'd, very nice image quality, no distortions, very uniform illumination. But these are all image features that are important for humans. So now, when you see it in the light of this, then you can really go back here and question, okay, can I do something? Can I make my my models cheaper? Think about Africa or India, where they simply do not have tons of $10 million or $3 million, whatever it is. Can you build simple, low-cost things that still give you a diagnostic information? And one of the things that we have a prototype 0.55T system at NYU. So that's substantially below the field strength of a clinical magnet. So this, for example, you could use or envision as a screening tool, fast imaging in third world countries. NIH has the same system, by the way, so we were not the first to have this system. NIH has this for a year. And so this is just a set of preliminary experiments we have from there. So one problem that you have there simply is you don't have enough SNR. So the SNR is much lower. You can combat this by doing multiple signal averages, but then your sequence takes, I don't know, 20 minutes, an hour. And so, for example, this is how it looks like on this system with 6 averages. This is how it looks with 1 average. And then you can train a reconstruction model, but using this as the target. And then you get something like this. Structural similarity is a lot better. I leave you to what you make with this information, if you think this is relevant or not. You can combine this with undersampling, and our goal here was to get this measurement in under 1 minute. So the fully sampled 6 averages takes 15 minutes. This is the image quality you got. And then if you do a single average under sampling factor of 3, you get down to 0.9 minutes. And this is the result we get. It's not as great as this one, obviously. Is it diagnostic? For some questions, it certainly is. Right? If you think about hydrocephalus or midline shifts, Alzheimer's disease, so these are very global. Also, it's unfair to compare this to a $10 million, 7 Tesla research magnet, but maybe compare it against CT. And then the question is, will this have value? That's pretty much open. But I think it looks pretty promising. Okay, to sum up, I hope I have convinced you that with modern math, computing, machine learning techniques, we really have an opportunity to rethink the entire diagnostic chain and then specifically go back from what we are really interested in, like try to see which clinical question do we want to answer, and then with that in mind, optimize everything back through the reconstruction hardware. And for the machine learning people, obviously this is very nice because this is essentially backpropagation. Lots of open questions, still very early growing field. Will it ever be robust enough for clinical question, for clinical routine, up for assessment? Even if it's working, can we integrate it in the clinical workflow? There's a depressingly high number of great techniques that did not make it into clinical practice simply because they were not compatible with what radiologists, doctors are used to doing, and it may be as simple as the operating system of the viewer that they use to look the images. So, but it will take time. I think if something is promising, it will make it in the clinical workflow and overcome this. Validation, right? So are we getting the right results? Are we getting clinically usable results? And that is going back to theory in the end, because we really, if you talk to people like the FDA or regulatory bodies, they are often afraid of machine learning, deep learning, because it has this black box stigma. Like you don't know what's going on in there. Is the pathology lost somewhere in the decision chain? And the more we can contribute to understanding the properties of these models, quantifying uncertainty, exactly like you said, the more people will be ready to adopt these technologies in practice. So with that, I want to thank my group and collaborators at NYU, collaboration partners at Graz, Facebook, the scientific advisory committee we had for the challenge, and my funding sources. Thank you.